Alright, so we are up to, in that first topic, which is the functions and graphs topic, we're up to what's called parametric equations. So parametric is when we have what's known as a parameter. So we're used to having things like x and y. Sometimes there's something else that might link the x and the y together. So time, for example, could be something involved. So parametric equations. So parametric equations, as I just said, they link variables together using a third variable called the parameter. So, circles, for example. I said often, so time is a parameter. So if you think about something, circles, you've got a circle and you've got an object moving around that circle, then wherever that object is, changes with the time, depending on what the time is. Depends on where the object is. And then if we're having an x and y axis, a Cartesian plane, so then the x value and the y value of any particular point depends on the time it is that this thing's been moving around. Alright, so if we put those things together, so circles, so we're looking at where the circle with the centre at the origin, and radius A. Is described by the following parametric equations. All right, so the x coordinate would be a cos t. Because if you think about, if we've got a point that's there, then the x value, the radius is a, then the x, that one there, if we, I said that's time, but if this angle here is in terms of time, then that's cos for the x, and so for the y coordinates, it's then sine. Alright, and so this is really quite simplified. There may be some other number with the t to indicate, I guess, how fast the thing's moving around the circle. But it's certainly the time involved. And we get a full circle, excuse me. We get full circle when t is between 0 and 2 pi. You get a whole circle. So we've got the time here being measured in terms of pi seconds rather than what you might be used to in the past about when you're measuring your time. So if we do it here in terms of pi, then we've got our time seconds, pi lots of seconds, then relates to kind of a radian angle. All right. Seems a bit complicated, but it's not too bad if you just think about the mathematics and go through the mathematics rather than worrying about this time being seconds in terms of pi equivalent to radians. All right, anything about that you want? So we might then need to put this back into a Cartesian form. So we can combine these. So this t here is our parameter because this t then links particular x and y. So for time of say pi seconds, then there's a particular x and a particular y value that will link together. So let's have a look at an example. I don't like how I've done that, so I'm going to split this board in half, so hopefully that's better. All right. Is that halfway? Okay, so angle, circle. So these parametric equations in this example, they're a little bit, an extra element to them that I didn't have in that basic. One, so here now I've got a 2, so rather than, so all that indicates is that rather than the centre being at the origin, the centre's going to be somewhere else. The radius is 3. And then we're linked to time from the angle. And so the y in this one is 1 plus 3 sine t. And again, so as I said, the centre's no longer at the origin, it's now somewhere else. And so the time, of course, is between 0 and 2 pi. Alright, we want to find a Cartesian equation. So to find the Cartesian equation, what we need to do is we need to eliminate the t, the time. Alright, so now, with this we've got sine and cos involved. And so one of the ways that, or part of what we need to use, is we need to use the fact that sine squared t plus cos squared t is equal to what? 1. So we need to play around with each of these things so that we can get sine squared and cos squared, and then we can put them together. So let's have a look at that. So for this x, alright, so first of all, before we can get the cos squared, we need to rearrange to get the cos t by itself. So to do that, we need to move this 2. And hopefully we could subtract. And then we've got this 3 out the front, and what do we need to do with the 3? Divide it, yeah. So ultimately we want cos squared. So all we would then need to do is square both sides, yeah? And x minus 2 squared over 9 might work. Alright, then we'll do the same with the same process with the y. Move the 1, y minus 1, divide by 3. Alright, slow me down if I'm going too fast. Then to get the sine squared, square both sides. And then we can add the sine squared and the cos squared together. So in terms of what I've got in this bottom line here, sine squared t plus cos squared t is equal to y minus 1 squared over 9 plus x minus 2 squared over 9. Yep, so it's just using these two. But then of course we know that sine squared plus cos squared is 1. So that means this left hand side here, that would be 1. And then finally, what we could do is what's this mean? The 9 times everything by 9. Yep. And so, what do you got there? Equation for a circle. Yep. So here we've got the circle, which is centre, is at 2, 1, and its radius is 3. Alright, so parametric equations with the t in it, Cartesian equation with no t. Alright, so note, in general, what we would have is x equals h plus r cos t, and y is k plus r sin t, using centre would be at h and k, and the radius is r, if you like. So I used the a before for this number in front here. A is of course the radius, so you don't want to use it. So using symbols that relate to the Cartesian and the parametric, that's what you can use if you like. Alright. Alright, so they don't have to necessarily do like that. You can have other variations where you've got parameters. So for example, find alright, so again you can have some sort of random, if you like, parametric equations. So again we've got t's in there, t is our parameter. We need to eliminate the parameter. So when you look at these, what do you notice? Anything in particular? One's got a t squared, the other's got a t, is what I first noticed. So, what could we do? Could we change this one so that it gets a t squared in it?
Square the y. Square the y.
Square the y. Alright, so if we square the y, we go y squared equals 2at squared, so y squared would be 4a squared t squared. Now, this one here, x equals at squared. If I divide by a, I'll get t squared. Yes? Now what?
Substitute the...
Substitute, yeah. So take this stuff here, put it in there. So we've got then that y squared equals 4a squared x over a, which then becomes y squared equals 4x. What happens with the a's? This one cancels with one of those, leaving just one. Is that correct?
Yep.
And so there's our Cartesian equation. You want to know what that represents? Sideways parabola.
Oh yes, it's y squared.
Because it's y squared, yeah.
Yeah.
Alright, so there's all sorts of other parametric equations that we can look at. So there's certain parametric equations for ellipses. So for example, I spelled that wrong. No, I haven't. This looks weird. So for an ellipse, so the ellipse x squared, whoops, on A plus y squared on B squared equals 1. has x first. X equals a cos t and y equals b sin t. So very similar to the circle ones. The difference being that our semi-major and semi-minor axes, you know what they are? No, they're these axes here, these lengths here, are different for an ellipse. So that's what you get. If you were to then, you would use the same technique as we did before, getting cos squared and sin squared, if we wanted to get a Cartesian. Hyperbola. So let's have a look at the hyperbola. And of course, hyperbolas have a similar equation to the ellipse. There's a minus here instead of a plus, and so they're parametric equations. Actually, I forgot to put. Oh no, it's all right. Their parametric equations end up being this. A sec t and y is b
A is
tan.
still the radius.
A is yeah, axis, yeah.
Axis.
Semi-major, semi-minor axis for the A and the
Oh,
B, yeah.
yeah, that's right.
And this time, your time, it's a bit more tricky to get the whole hyperbola because there's values of tan sec that are not defined, so the restriction is this, not square brackets, curved brackets from negative pi and 2, I think it's right, to pi on 2. Because pi on 2, those things are not defined. And the union with pi on 2 to 3 pi on 2. That gives you the whole hyperbola. Yes? All right, a couple more, actually 3 more examples.
3.
3. first one. So we're going to turn, this is a Cartesian, we're going to turn it into parametrics. So what do we know about parametrics? So this one, where's the centre of this one?
0,
0, 0, it's at our origin and our radius. Right. So because we've got 0, 0, we've got that version there. A cos t, A sin t. And the radius is 3, so 3 cos t, and y is 3 sin t. Yep. So the next one. So what do we got here? And ellipse. So we've got an ellipse. And so for this ellipse, the centre, 0, 0. A. So what's the A attached to, or associated with, I should say? A is associated with X or Y? With X, yeah. A comes before B in the alphabet, so does X come before Y. So A is 16. 4, thank you.
Yeah.
Just making sure you're awake. So B is 2. So our parametric equations, x equals A cos t, y equals B sin t. And instead of putting the B there, I need to put 2. All right, the last one. All right, what do we got? Got a hyperbola. And so we've got something else that's going on with this hyperbola. And that's that the centre of this hyperbola is where?
1 and -1.
It's at 1 and -1. Now I was a bit slack before because I didn't give you the version of the parametric equations which have that central point of our hyperbola. And I didn't do it for the ellipse either. So A should be 3 and B should be 2. So this translation effect, when we do our, we have 3 sec t. And how's this translation in the x direction of 1, how are we going to represent that in there?
Is it plus 1?
Plus 1 or 1 plus is how you would often see it used, yeah. And so for the y, that's got to be 2 tan t, and you might have it as minus 1 plus, or two tan t minus 1. Alright, so originally in those notes when I put those parametric equations, I didn't put that translation of the centre in there. But it's pretty straightforward how it goes in. Just goes in straight away. Alright, anything about any of that? And the other thing that I should have is perhaps restrictions on what t is, so we get the whole circle. Other than that, no questions? Nothing I need clarifying? No? Alright, so we're now up to problem set number 5, which is the exercise 1H stuff. Should be on your work plan.